really welcome. I want to say today's going to be a lot of fun. It's one of my favorite days of the winter school because I am going to try and stretch you guys mentally, and we might even do some physical stretches as well, depending on how the session is going. But I want to stretch you guys mentally in one of the most interesting but also intriguing topics that you'll ever come across in mathematics. And that is the topic of differentiation. Okay? The reason why I chose differentiation to do with you guys today is, together with yesterday's functions and graphs, which we are kind of also going to look at, is going to count between 50 and 60% of your paper 1. Okay? 50 to 60% of your paper 1 is going to consist of differentiation and functions and graphs. So, it's kind of important. Ladies and gents, for those of you that have AP Maths, I know a lot of the things that I'm going to do is going to be very trivial for you. And for some of you are going, so I wish that was me. Okay. Some of you are regretting that your school doesn't do AP Maths or you never did AP Maths. But ladies and gentlemen, the whole exercise of today is not just can you differentiate, can you solve for x, can you draw a graph. The whole process of today is, are you able to understand what differentiation means? Because you are going to be stretched for where they test how does these things fit together. What does it mean? How does it work? Because as I said yesterday, those of you that have these fancy calculators, I want to find one, here we go, that has these fancy FX991ZA, that's the new fancy one, okay? They want to try and move away from that. So they want to more grasp, do you actually get what is asked? So that's where we're going to go today. So I would like you guys to go on this journey with me. But please don't feel stupid. I'm saying it in advance. Because I am going to ask some questions that you have never thought about. And I'm going to make some statements you've never heard. Because that's just the way I am. So ladies and gentlemen, my first question, thought-provoking question for the day, what is differentiation? That's our first thought for the day. Now you guys have all differentiated. Is there anybody that hasn't done differentiation at school yet this year? I hope not. Okay, thank you, that's great. Now everyone has done it. What is derivatives? If I ask you, determine the derivative of the function, what does it mean? Okay, is somebody willing to answer? Yes. Say again though. The gradient. Okay. Let me say this. You've got the right idea. That's the one application of it, is gradients. But what does it mean? The rate at which it's done. It is done. The rate at which it is done. What is the it that you are talking about? Because the it for me is a scary clown. Just whatever the one variable. Okay. You're getting very, very close. But now, the problem is, you guys have been doing rates of change since grade 9. Huh? You've done gradient since grade 9. But then why do we need What makes differentiation different from rates of change or gradients that you guys have been doing since grade 9? Come on. Anybody? Someone said a tangent to a graph. That's, again, an application of it. But now the question is, why do we need derivatives if we've done gradients since grade 9? Come on, grade 12s. Come on. Okay, let me take a load off your shoulders. Ladies and gents, differentiation gives you the rates of change at a point. It gives you the rate of change not between 2 points, but the instantaneous rate of change. That's my beautiful, lovely definition of differentiation. The instantaneous rates of change. Now, who can tell me why is that important? Why is it important to have the instantaneous rates of change? Why is it not enough to get just a gradient between 2 points? Say again? What about changing? A graph could be continuously changing, yes. But let me explain this to you by drawing a graph. I love my graphs. Let's say I get the gradient between 2 points. So in what would you like to become one day? Mechanical engineer. Okay? Now some of the people are going, woo! Okay, so you want to work in cars, I'm guessing? Cars, engines, developing engines, those kind of things. If you're talking about the heat distribution in an engine, and you look at a graph that looks like this. Let's say, for instance, you go and you say, ooh, the graph, the car heated quite a bit from beginning to end. But it's not so bad if you look just at that gradient, for instance. But actually what happened was this. That doesn't look good at all. Okay? All of a sudden, you can say, but whoa. Why is the engine cooling down so much and then all of a sudden it's got a very big heat increase, then it cooled down? What the hell's going on in this thing? But that is what differentiation is all about. Differentiation, and the reason why we need it is so we can get a rate of change at a point. In other words, what's happening to a graph at a specific point. For those of you that are interested in life sciences, biology, you don't want to take just an increase of a population over 5 years. You want to know at a specific point what is happening to the populations. Are they increasing? Are they decreasing? Are they stable? What's going on? Those of you that want to go into economics, you want to know at a specific point, is my revenue or my loss, what's happening to it? Is my income becoming more? Is it becoming less? You don't want to wait a year and go, oh yes, ooh, it decreased. That kind of defeats the purpose. That's why differentiation is so important. Now I'm going to make a very bold statement. The statement is as follows. The past 12 years of your school career has led to differentiation. Everything you did in the past 12 years have brought you to differentiation. When you go to engineering or studying calculus in any course, Everything builds up towards integration and differentiation. All the exponential laws you did so that you can apply it in differentiation. All the trigonometry you've done, you're going to apply in differentiation and integration. Guys, everything you've done, except maybe for geometry. Geometry is like the black sheep of the maths family, okay? You never look at geometry again when you're past maths, unless you study pure maths. But all the other topics is going to lead towards differentiation, even finances. When you get to second, third year, if you study the maths behind, say, the economy, you do calculus, differentiation, integration, as much that it comes out of your ear. So, it's relatively important that you understand it. Okay. So now the question is, when I look at differentiation, now, when I look at differentiation as being the rate of change at a specific point, because that is basically what differentiation is all about. The rate of change at a point. It is important that you not only can differentiate, but that you understand what's happening. Is the graph going up? Is it increasing? Is it decreasing? Or is it stable? It's stationary. But the important thing is as well your notation. I'm honest that I say it grinds my gears when kids don't use the right notation, because if you use the wrong notation, it means something completely different. So if I've got y and I want to differentiate, then I, for instance, am going to say dy over d, whatever your independent variable is. It could be dy over dt. It could be dy over dx. It could be dy over dp, depending on your variable. It's not always going to be dy over dx. You've got to be careful. If it is f of x, my derivative is going to be f accent of x. Do not confuse it with f to the negative 1 of x. Okay, be careful. You have to be careful because f to the negative 1 of x is something completely different. But what is the difference? Let's start with f of x. We did f of x yesterday, ad infinitum. Okay, meaning a lot. What does f of x give me of a function? Say again? I heard it somewhere, yes? The equation, and the equation gives me what? The y values. So if I talk about f of x, I am talking about the y values of the function. If I talk about f accent of x, what am I talking about? F accent is the derivative, and the derivative gives me the, what did you say at the beginning? The gradient of the graph. And what does f to the negative 1 give me? The inverse, or the x values. Okay? So your notation is important. I'm going to throw a horrible one in for you, sir, that I've seen them ask just to confuse you guys. But what about 1 over fx? Say again, what did you say? Ooh. It is the reciprocal of the function. You've got to be careful. This is the reciprocal. And now you guys are like, But sir, that's the same thing. No, it isn't. Let me explain to you. Let's say I give you f of x being 3 to the power of x. What is f to the negative 1? I swap y and x. So I've got x equal to 3 to the y. And if I rewrite this in logarithmic form to get y alone, I have log base 3 of x. But what is the reciprocal? This is 1 over 3x, which is 3 to the negative x. Definitely not the same thing. You've got to be careful that f to the negative 1 does not mean reciprocal, it means inverse. Now I would like to ask you guys, but what does f double accent of x mean? It's the second order derivative. And what does that give me of fx? That is a test for a minimum or a maximum. But it is just an application. But what does f double accent x give me? Yes, sir. Okay, again, you guys, I'm getting a trend here. You guys are getting confused between what something means and an application of it. Because yes, my gente in the front said, it's the point of inflection. That's an application of it. Because an application is if the second order derivative is 0, then it's a point of inflection most of the time. Going to show you an example when it is not. Yes, sir?
Rate of change of the rate of change.
Rate of change of the rate of change, which gives me concavity of the graph, which is the graph, so f double accent is the concavity of the graph. In other words, does it look like this or like that? I like to think of it as acceleration. Is the graph accelerating or is the graph decelerating? And now some of you are going, sir, do you really need to go towards physics in this? Do I need to go to physics in this? Does that kind of look familiar to you guys? Okay, let me quickly bedazzle you guys. If I differentiate this thing in terms of delta t, I take the 1 Morse and I bring it to the front. So I'm left with Vi plus 2 times pi a half is 1. But sir, that's final velocity. The derivative of displacement is velocity. But what if I differentiate velocity? Well, that is a constant, and if I differentiate a constant, the answer is 0. So what am I left with? Acceleration. Oh, but sir, why did you have to bring physics in this? Because physics got it from maths. Just putting it out there, no one, not preferential towards one, but the maths gave me the physics. Ladies and gents, I want to ask you guys, a really silly question. But it's still a good question. Why, when I differentiate a constant, is the answer 0? I would like to ask you guys that. Who can tell me? Are you willing to try? Why? Okay. I like that you're thinking about graphs. I love it. But I think let's extrapolate. Let's go bigger. Because she's saying big words. If I use two big words like extrapolate, just go, wait. What does it mean? Guys, extrapolate means to go away from, or to build upon something. So I'm going further than what she's saying. Guys, what does differentiate give me? Constantly think. What does differentiation give me of a graph? Rate of? Can a constant change? So what is the rate of change? 0. That's why when you derive a constant, the answer is 0, because it's a constant. It can never change. Oh, I never thought about it like that.